John is going to tell us about the image of the trivial source ring in the ring of virtual characters of a finite group.
Thank you, McHugh, for the introduction. And I just wanted to say on a personal note, it's always been a dream of mine to go hiking in the Swiss Alps, and I never thought that studying math late at night in my bedroom. So thank you for inviting me. Yeah, I'm going to talk about a problem. It's basically a character theory problem, but its origins come from modular representation theory of finite groups. So I'd like to start by describing the problem, although maybe it's been a while or maybe you've never seen modular representation theory before. So if you don't understand the setup for the problem, that's okay, because really the point I'd like to get across today is the method I use to solve the problem and the language the solution is written in, which is the language of biset functors. Anyway, I'll come to that. So throughout G is going to be a finite group, and K will just be an arbitrary field of characteristic 0 for now. Later in the story, it'll be a specific field. I'll denote by ir K of G, like others before me, the set of irreducible characters of KG modules. And then I can create a ring out of this set, Rk of G. As an abelian group, it's free with basis the irreducible characters. So that means now I can add or subtract characters. Such things are called virtual characters. You can also multiply them as well. So Rk of G is that ring of virtual characters. And if I had a field extension, if K was contained in L, then I could view a character of a KG module as a character of an LG module just by extension of scalars. So Rk of G is a subring of RL of G. If, in addition, L is algebraically closed, I could define a subring of RL of G, R bar K of G. This notation comes from Sayre's book on linear representations of finite groups. And it's the subring of K-valued virtual characters. So of course, if you're a character of a KG module, then you take values in K. So you have this containment. But it can happen that this containment is proper. I'll show you an example. This is a kind of a toy example, but it'll turn out to be very important to the story. This is the character table for the quaternion group Q8. 4 linear characters and 1 irreducible character of degree 2. So that means if I computed this ring of virtual characters over the complex numbers, as a Z module will be free of rank 5, since there's 5 irreducible characters. Looking at the table, you can see everything is Z valued. So every virtual character takes values in Q. So this subring R bar Q is actually equal to the whole thing. Now, lambda 1 through lambda 4, those are linear characters, so they're actually group homomorphisms. Since they take values in plus or minus 1, they are realized over the rational numbers. So all of these things, these are characters of rational representations of Q8. It turns out, maybe it's a good exercise, this last character, the degree 2 irreducible character, is not realizable over Q, but 2 times it is. So I'll call this character psi. This is sort of the villain or the hero of the story, in your point of view. Psi is not an element of RQ, but 2 psi is. And so therefore, if you were to compute this quotient, you would get Z mod 2Z. So this will also turn out to be important. Maybe I'll write it here or here. So RQ this is isomorphic to Z mod 2Z. And it's because there's this one bad character sticking out. The elements I can think of as 0 and psi. Of course, this is actually the coset containing psi, but okay. All right, now for the modular representation theory. Let O be a complete discrete valuation ring whose residue field K is algebraically closed of positive characteristic P. This is sort of how a lot of papers in modular representation theory start. A ring like this kind of bridges the gap between the characteristic 0 theory and the characteristic P theory. Okay, so an OG module is called a trivial source module if it's a direct summand of a permutation OG module. It's a very nice class of modules to consider for your finite group. I could explain more later if someone asks. So just like you can create the ring of virtual characters of a group, you can create this ring, a ring of virtual trivial source modules. Maybe you think of the elements not as characters, but as like isomorphism classes of trivial source modules, and you're allowed to add and subtract them and multiply them. Multiplication comes from the tensor product. Okay, now I said K was going to be a specific field later on. Set K equal to, this is the notation, I think that comes from algebraic number theory. What it actually is defined to be, it's Q adjoin all roots of unity, complex roots of unity that have order prime to P. So you might denote the set of such roots of unity by mu P prime, and then that's what you get. So you fix your prime P, adjoin all, I assume everyone knows what I mean when I say P prime. P prime roots of unity to Q. Okay. Now, an old theorem of Dress from the 70s states that the character of any trivial source OG module actually belongs to this ring of virtual characters. So if I take the character of a trivial source module, I land up in this ring. And taking characters is actually a ring homomorphism from this Grothendieck ring to this one. This is the ring homomorphism I'm interested in. And the question I would really love to answer is, if I start with a character here, by the way, in Isaac's book, for example, such characters are called p-rational characters. So if I start with a p-rational character, how can I determine if it's the character of some trivial source module? In other words, I want to know if I start with an element here, when is it in the image? Another way to phrase that would be, when is the image surjective? Or even better, I could ask, what's the co-kernel? So this is what I'm interested in, and actually I think this is a good place to start because this thing can actually be computed in GAP. Okay, that's the end of the sort of setup for the problem. So if that didn't make sense, it's probably my fault because I'm trying to go quickly. But just keep in mind, the problem is you start with a finite group G, and associated to it, I guess you also need a prime P. Associated to those two things, I've got this quotient that I'm trying to compute. That's all. So it's a abelian group attached to that setup that I want to know. All right, so now I go into GAP. And I'll start with the smallest prime, p equals 2. And I ask GAP to compute this quotient for all small groups. In this table, I've listed the groups that GAP finds for which this quotient is non-zero. So the first group where this quotient is non-zero turns out to be Q8. And the table is sort of striking. First of all the entries here are just vector spaces over Z mod 2Z, finite dimensional. And you might also notice Q8, Q16, Q32, the generalized quaternion groups are showing up. In the other groups, the quaternion groups still seem to play some role, like a CeLO2 subgroup of SL23 is Q8. There's C3, semi-direct Q8, C3 cross Q8. So it looks like the value of this quotient at Q8 is somehow influencing all the other quotients. Any other group that appears here has some relation to a generalized quaternion group. So now from these computations, there's one conjecture to work towards. Okay. Now let's move on to the first odd prime, p equals 3. If I run the same program, GAP doesn't find any examples for which the quotient is non-zero. And if I try another odd prime, I don't find any. That doesn't mean at this point that there aren't any. It just means I tested groups up to like order 300 or something and didn't find any. For p equals 2, there were tons of examples. For these odd primes, none. So now that's another conjecture. If p is odd, this ring homomorphism should be surjective. Now, looking at that table for p equals 2, the first group that shows up is Q8, which is a 2 group. So it suggests maybe we should take a look at what's happening at p groups. Let p be an arbitrary prime number, and again, I'll remind you, k is Q adjoin p prime roots of unity. Now here's 3 facts. One was proved by Brouwer a long time ago. Remember, you always have Rk of G is contained in the ring of k-valued virtual characters. The containment could be proper, but for this specific field, it turns out it's not. So if you know the theory of Schur indices, it means Schur indices are always 1 over that field. Okay. Then a second fact, if p is a p group, okay, when I compute Rk of p by fact 1, it's the same as computing R bar k of p. And then if you think about it, well, K is just Q adjoined P prime roots of unity. So a K valued virtual character for a P group is the same thing as a Q valued virtual character. So I get that equality. Now the third theorem, well, third fact is it follows from two theorems, the Ritter-Segal theorem and the theorem of Dress from before. If P is a P group, then the image of this ring homomorphism I'm interested in is precisely the ring of virtual rational characters for the P group. So put these facts together, what you get is, if I compute the quotient, the co-kernel I'm interested in at a P group, it's the same as computing this. Because, well, it's actually equal, not just isomorphic. Rk of P is actually equal to that thing, and the image of kappa is equal to that thing. So this explains why, when I took P equal to 2, and I computed this quotient at Q8, a Z mod 2Z appeared, because of that toy example we did in the very beginning. There's this bad character psi that's sticking out. Okay. So let's see. Okay, yeah, so when I'm computing this quotient at a P group, really I'm computing this quotient, and it turns out that this thing has already been studied by Roquette in a paper from the 50s. I think it was written in German. I don't know, it was about Roquette. Let P be a P group. If P is odd, then this quotient is 0. And if P is even, and this quotient is non-zero, which is possible, then Q8 is a subquotient, and this thing is always a finite dimensional vector space over F2. It's the exact same phenomena we were observing in our general tables, but Roquette only tells you what's going on for P groups. And of course, his perspective was not thinking about the trivial source ring. He's just looking at R bar Q mod R cubed. So now there's kind of a perspective change. At first I was interested in fixing a group G and a prime P and computing this thing. But based on the computations and knowing this theorem, it seems like the value of this co-kernel at the P groups somehow influences what's going on everywhere. So rather than fixing a group G and computing that co-kernel, I'd rather look at all groups and think about the value of this thing at every group and focus special attention on the P groups. The way to make that formal is by using the language of biset functors. So I'm not going to try to give the actual formal definition because I think having an intuitive informal definition is better for this stuff. So let's start with K, a field of characteristic 0, for example, this field we've been using. My advisor Robert Bolche and Olje Josh Kuhn, building off of ideas of Serge Buch and others, have defined a pre-additive category C. The objects of C are all finite groups. And the category C, the pre-additive category C, possesses morphisms, you can think of them as just arrows, that symbolize our favorite operations from representation theory. So for example, there are arrows in this category called induction, restriction, inflation, deflation, transport by isomorphism, and multiplication by a linear character. The morphisms satisfy all expected relations, like induction is transitive. Now let me draw a picture. So here's what C looks like. Big circle. Within this category are all finite groups. So maybe I've got an S3 here, an S4. There's a Q8 over here, a Q16, C3 cross Q8. And then there are morphisms that represent our favorite operations. So for example, S3 is a subgroup of S4. So there's an arrow pointing from S3 to S4 called induction, from S3 to S4. There's also one from S4 to S5 called induction. And if I were to compose these two arrows, I'd get a third arrow called induction from S3 to S5. Okay, so this is like the informal definition. Now, what is this category good for? on it, we can define things that are called k-cross fibered biset functors, or just biset functors, which are additive functors from this category to the category of abelian groups. An example of such a thing is the functor which takes a group, let's say S4, and maps it to the virtual character ring at S4. So instead of computing the virtual character ring for a given group, what I'm doing now is thinking of computing it for all of the groups at the same time. So this is what this functor, which I meant to note like that, does on the objects. You plug in a group, you get the virtual character ring associated to that group. If you plug in a morphism, like this one called induction, you can guess what's going to happen. You get the morphism given by, you plug in a character, you induce it to S4, and you get the element there. So that's what this functor does to morphisms. So a biset functor is like a way of categorifying the construction which sends a finite group to the virtual character ring, or any other Gromdik ring you might associate to a finite group. And it categorifies it in such a way that all of your favorite operations are also involved in the game. Okay, so RK is an example of a fibered biset functor. Biset functors, actually, they turn out, because the target category here is an abelian category, biset functors form an abelian category. And so I can quotient one biset functor by another. If K is this field we've been working with, RK mod the image of kappa is another fibered biset functor. Remember, this is the thing I'm interested in computing. But now, like I wanted to, instead of computing it just for one group, I'm viewing it as a functor and trying to figure out the structure of this functor. So here's how you complete the problem. Let K be as before. C will be this category that I've drawn. And then I'll let C sub P denote the full subcategory of C whose objects are P groups. So in this picture, if P was 2, maybe I could separate the two groups here. So actually this would be C2. The whole thing is C. Based on our observations from the table, what we think is that the whole functor, RK mod the image of kappa, is somehow determined by its restriction to that subcategory. So that's what I've written here. RK mod the image of kappa is determined by its values at the P groups. Well, if I can restrict a biset functor using some abstract nonsense, I can also induce biset functors. It's not the induction you're used to using, you're inducing a functor. So by adjunction, because induction and restriction are adjoint to one another, there's a natural transformation. If I restrict this thing I'm interested in down to the P group category, induce it back up, there's a natural transformation to the original functor. And the main theorem I was able to prove is that this thing is surjective. Okay, it seems like a lot of abstract nonsense, and it kind of is. But it turns out all of the observations we made in the gap computations fall out of this one compact little theorem. So for example, we've already seen, if I compute this quotient at a P group, it's the same thing as computing this. Roquette's theorem said if P was odd, this thing is 0. So when I restrict this functor, I get the 0 functor. If you induce it, it's still going to be 0. And because this is surjective, that thing is 0, which gives you immediately that kappa is surjective in case P is odd. Also, Roquette said if P is 2 and you compute this thing at a 2 group, it's always a finite dimensional vector space over Z mod 2Z. So same type of argument. If you induce and then map surjectively, this thing, whenever you plug in any group now, you'll get a finite dimensional vector space over Z mod 2Z. That's the basic idea. Now, to finish it up, using Serge-Bouc's theory of rational P biset functors, which would take too long to explain, we can show that this functor, defined just on the subcategory whose objects are the P groups, is generated by the unique nonlinear character psi of Q8, that bad apple. What that means is that if let's draw a picture. if I have some other 2 group P, and I compute this quotient, maybe it's non-zero, maybe there's some element, I think I called it theta there, yeah. Maybe there's some element theta here. Well, that theta is actually nothing new. It comes from psi. Psi was the non-zero element here, and I can get from psi to theta by applying some combination of induction, restriction, multiplication, inflation and deflation, etc. Yeah, sorry. Okay, since eta is surjective, this thing is also generated by psi, and so we deduce all of the conjectures we made in the beginning. If this quotient is non-zero, then the group G has to have a subquotient isomorphic to Q8. When P is equal to 2, and you have some element in this quotient, in the cokernel, the theta actually comes from psi. So all of the groups that appeared in that table for P equals 2, all of the, if you think of those cokernels being non-zero as a problem, the source of the problem is this bad character. Lastly, what we hoped for originally falls out of all of this. There's a detection theorem. If you have a p-rational character, it's in the image, it's the character of a trivial source module, if and only if its restriction is in the image of kappa for all subgroups satisfying a certain condition. Okay, thank you. Sorry I went over time.